Let's welcome Professor Brian Greene.
Thank you very much. It's a great pleasure and honor to address you this afternoon. For a long time, the word universe was taken to mean all that exists, everything. And what's happened in the last few decades is that scientists have begun to think that what we have long thought to be everything, to be the universe, may actually be a small part of a much bigger, much grander, much wider cosmic landscape. And that larger cosmic landscape is what has come to be known as the multiverse. And what I'm going to do here in the brief time we have today is tell you 3 short stories, each of which in its own distinct way draws our attention to the possibility that we might actually be part of a multiverse. This will not prove that we are in a multiverse. It simply gives us strong motivation to take the idea seriously, as many scientists around the world currently are. So I'm going to jump right in to the first of these stories, and one common feature of all of them is that they rely on an understanding of the force of gravity. Now, the force of gravity is a force that was first described mathematically by Isaac Newton way back in the late 1600s. He gave us a little mathematical formula that we can use to predict the motion of planets in orbit around a star. And the amazing thing is, we use this little piece of mathematics that we still teach to high school kids around the world. You all know it, right? F equals G, M1, M2 over R squared. Little mathematical equation that fits perfectly on a t-shirt. And using that piece of mathematics, we can predict where objects should be, and we look up into the night sky, and they are just where the math says that they should be. So this was a vital step forward in our understanding of gravity, the most pervasive force governing the happenings in the cosmos. But even so, Newton left something out. He never told us how the force of gravity works, how it's communicated from one point to another. How does the sun keep the Earth in orbit? We call it gravity, but what's the mechanism by which gravity gets the job done? And that was a question that resisted solution until Albert Einstein came along, and he gave us a new way of thinking about gravity. He said, think about gravity. It's not a perfect analogy, but it's a pretty good one. He said, think of it as if you have a rubber sheet stretched in front of you, nice and taut. Now, if you roll a marble on the rubber sheet, it goes in a straight line trajectory. Nothing too confusing about that. But if you now take a large object, like a rock, and you put it in the middle of the sheet, now the sheet will be curved. It's warped. And if you send that marble rolling along its surface, it doesn't go in the same straight line trajectory any longer as it did before. Now the marble goes in a curved trajectory because it's rolling on the curved surface of the rubber sheet. Einstein says, take that idea and apply it to the universe in the following way. Instead of a rubber sheet, think of the fabric of space. Now, this is a 3D image of space, a little hard to process fully, so I'm going to go down to a 2-dimensional image just like the rubber sheet, and you see it's nice and flat when there's nothing there. But if you bring in a body like the sun, the fabric warps. And then the Earth is kept in orbit because it rolls along a valley in a curved environment that the sun creates. And the Earth, too, it also warps the environment. And the moon is kept in orbit because it is rolling along a valley in the warped environment that the Earth creates. That's the mechanism, according to Albert Einstein, and how gravity is transmitted from one place to another, warps and curves in the fabric of space and time. Now, 1919, this idea is proved through astronomical observations of the curved trajectories taken by light beams during a solar eclipse. And with that confirmation, Albert Einstein becomes Albert Einstein. He becomes the most revered scientist in the world. And because of that, others begin to take up his ideas and try to push them forward. And one individual in particular is this fella right over here, Georges Lemaitre. He's a Belgian Jesuit priest who had the unusual distinction of not only being a priest, but also had a PhD from MIT. And he took Einstein's equations and applied them not to an object like the sun or the earth. He applied them to the entire universe. And he found, surprisingly, that Einstein's math would not allow the universe to be static, unchanging, eternal. That was inconsistent with the mathematics. Instead, he found that the universe either had to be shrinking or stretching over time. Now, Einstein resisted this idea. He had the philosophical prejudice that on the largest of scales, the universe should be unchanging. It always was and always would be. And that perspective changed because of the observations of this fellow right here, Edwin Hubble. An Oxford-trained lawyer, turned out to be a fantastic astronomer when he changed careers. And he found, using the powerful telescope at Mount Wilson Observatory, that the distant galaxies are all rushing away. The universe is stretching, it is expanding, just as Einstein's mathematics said that it should be. And with that, we come to the Big Bang picture of the universe. So early on, the universe is tight and compressed, and over time, it stretches and grows. And as it grows, it cools down. And as it cools, structures can coalesce out of the hot primordial beginning. So here we have a beautiful story that begins with simple mathematics in the hands of Isaac Newton, goes into a more complicated form by Albert Einstein, and then turns out to give us a picture of how the universe progressed from early on in its history right through today and into the future. But even so, even though that is a remarkable achievement, man, think about that. We humans, we have not been walking around this planet for too long, and yet we now have a mathematical idea that talks about the earliest moments. But what the theory left out, it didn't tell us what drove the outward push in the first place. And that's a deep puzzle that resisted solution for many decades, because if you think about it, gravity is the most powerful force on cosmic scales, but normally when we think about gravity, we think about a force that pulls inward, that pulls things together. That's an attractive force. If you want to go outward, you're going to need a force that pushes in the other direction. And in the late 1970s, scientists who were again studying Einstein's mathematics intently, they found in Einstein's math, gravity, it turns out, can have two forms. Gravity can be attractive, the form that you and I are used to, from living here on a clumpy rock called planet Earth. But the math also showed that if you don't have a clumpy object, but you have energy that's uniformly spread throughout space, that gives rise to a different kind of gravity. It gives rise to a repulsive gravitational push. And that energy, I like to think of it as a cosmic fuel. That cosmic fuel drove, we believe, the outward swelling of space. Now, this idea also comes with predictions. So what you're looking at here, this is the cosmic microwave background radiation, heat left over from the Big Bang. And the little color differences from pixel to pixel represent tiny temperature variations of on the order of 1 part in 100,000. Now, the mathematics says that if the universe underwent this rapid swelling from repulsive gravity, that little tiny variations in the early universe from quantum physics would give rise to tiny temperature differences. So there's a prediction for how the temperature should vary from point to point in the sky. And let me show you. Here is the prediction. This is a statistical analysis of the picture I just showed you. And here are the observations. So the curve is mathematics, and the yellow dot are actual observations. And I'll just be quiet. Wow. To me, this is as beautiful as any piece of art that anyone of our species has ever created. The fantastic agreement between a mathematical theory of how the universe started and our observations 14 billion years later of photons that have been traveling unimpeded since that creation moment that come to our telescopes and confirm that our mathematical theories are telling us how the universe got started. Now, I'm bringing this up because it fits into the larger theme, the theme of multiverse. Why? If this picture is correct, and the Big Bang came from this cosmic fuel giving rise to a repulsive gravitational push, the math also shows that it is virtually impossible to ever completely use this fuel up. Some of this fuel will drive our Big Bang, but there'll be leftover fuel. What does it do? It drives another Big Bang. And there's leftover fuel from that. What does it do? Drives another Big Bang, and so forth. Big Bang after Big Bang, giving universe after universe. So the picture then is like this. That's our Big Bang. Leftover fuel gives rise to another Big Bang, and another, and another, and another. And each of these spheres, these aren't planets or galaxies. According to these ideas, these are actual universes out there in the cosmos. Now, when you try to make sense of this idea, you find that if you try to push into the micro world, there is a problem that arises. In order to put gravity and quantum mechanics together, you need a new understanding of the micro world. And that new understanding involves a new idea called strings. So this is the second story. Down in the micro world, we are driven to a new picture of the fundamental ingredients of matter. Instead of the electrons and the quarks that you are familiar with from a cursory study of the makeup of the world, the idea is little tiny vibrating filaments may be what's at the heart of matter itself. And these little tiny vibrating filaments at the heart of matter is, again, a hypothetical idea, but it's a beautiful idea because it suggests that everything in the world arises from the different vibrational patterns of these little fundamental entities in the micro world. So in the macro world, we have Einstein's theory of general relativity giving rise to this mathematical theory of the Big Bang, this theory that gives rise to the possibility of other universes. And in the micro world, we're driven to a picture where the fundamental ingredients are little vibrating filaments. And a complication of the story is that the mathematics of string theory only works if the world around us has more than 3 dimensions of space. So we are all familiar with left, right, back, forth, and up, down. According to this theory of the micro world, there are more dimensions than that. So to get a picture of that, if we look at a familiar object, it has the dimensions we know about up, down, left, right, back, forth. But according to the ideas, if you zoom into the micro world, there are additional curled up dimensions into particular geometrical shapes. This is what's known as a Calabi-Yau shape. The Yao in that is Xing-Tung Yao, famous Chinese mathematician. Many decades ago, he was my teacher. And the idea is, according to the math, that the way the strings vibrate in the micro world is determined by the twists and the turns in the geometrical form of these extra dimensions. So the beauty of this idea is that if we knew exactly the shape of the extra dimensions in the micro world, we might be able to answer questions we have been asking for 100 years. Why does the electron have its particular mass? Why do the quarks have their particular masses? According to these mathematical theories, it all has to do with the shape of those extra dimensions. Now, when I was a student back in the 1980s, there were only 5 known candidate shapes for the extra dimensions. But then as people worked harder into the 1990s, they were able to find more and more possible shapes for the extra dimensions. From 5 in the 80s, it grew to tens of thousands, which is kind of okay because graduate students need something to do, right? But then, as the years went by, the numbers soared. Not tens of thousands, not millions, but today, there are about 10 to the 500 possibilities for the extra dimensions of space. So what do you do with that idea? Well, some people leave the field, think that the theory will never make any predictions because you need to know the shape, to know the vibrational patterns, and without being able to pick one shape out of this vast collection, nobody knows what to do. There's a different approach, though, one that ties into the theme of the multiverse, which is this. Maybe there is not one particular shape that's the right shape. Maybe all shapes are the right shape in the sense that maybe there is not one universe, but instead maybe there are many universes. And we can link this up with story number 1, because imagine with those multiple Big Bangs, the distinct universes produced by each bang has a different shape for the extra dimensions. So now I'll show you this again, but I'll augment it by showing you the shape for the extra dimensions associated with each of these universes. So I'm going to focus in on a collection of the universes and let you see what the shape associated to each would be. So our universe, say, might be the blue one here, that's our shape, but these other universes would have different shapes for the extra dimensions and therefore different properties for those physical features in that universe. Now, that's story number 2. Story number 3 is now going to put story 1 and story 2 together in the following sense. And this is the only part of my discussion as I get to the end of my remarks, which comes from observations that were made in our era. In the late 1990s, 2 teams of astronomers announced a result that pretty much shocked the community of physicists. Because we had known since Edwin Hubble back in the 1920s that the universe is expanding, as I discussed a few minutes ago. But everybody thought that sure, the space is expanding, but it must be slowing down in its expansion because the pull of gravity would cause each galaxy to tug on every other, slowing the cosmic exodus. So much as if you toss an apple upward, it goes up slower and slower. The belief was that the expansion of space would be slowing down over time. These 2 teams of astronomers who won the Nobel Prize for the result found quite to the contrary, that the expansion of space is not slowing down over time. They found that it's speeding up over time. The exodus is going ever more quickly. Now, how can you explain an ever-quickening expansion of space? Clearly, you need something to be pushing outward. And if you were paying close attention to the first story, I noted that in Einstein's theory of gravity, gravity can be repulsive. That's how we believe the Big Bang got set in motion in the first place. So the thought is that even today, there is an energy field called dark energy permeating space in this room and everywhere else, giving rise to an outward push that on the largest cosmological scales is driving the distant galaxies to rush away ever more quickly. The problem with this explanation, which will then bring in this idea of a multiverse to tie all the 3 stories together, is when we actually work out how much dark energy is needed in any given volume of space to explain the rapid accelerated expansion, the number is a very strange number. Here it is. A decimal point followed by 120 zeros and then a 138 at the end. Now, when we see a number like that, it kind of makes our collective hearts sink. Why? We want to explain the numbers that we measure. But the numbers in our formula, in our equations, are typically numbers like 1, square root of 2, pi, e, things of that sort. And it's hard to imagine how you can ever start with those kind of ordinary numbers and do a calculation and have this number pop out at the end of the page. So what do? Well, you could give up and simply say this is a number that's imposed on reality from on high, or an accident, or something that resists explanation. Those are the kinds of theories, though, that leave us deeply unsatisfied. Another approach, which is the most radical of all, is to make use of this idea of a multiverse. Because each of these different universes, if they have a different shape for the extra dimension from string theory, that shape will give rise to different physical properties, such as different values for the dark energy. So the idea would be that our particular number is there simply because with 10 to the 500 different shapes, it's very easy to get a number like 10 to the minus 120. It's simple, it's trivial in that case. And therefore, it's one other piece of evidence suggesting that our universe might not be the only universe. Could we test this idea? It's possible. So again, looking at the heat left over from the Big Bang that I showed you before, the microwave background radiation, here's the thing. If there are many universes out there, those universes on occasion can collide with each other. And if they collide with each other, the impact, say, on our universe from such a collision would send ripples going through this heat left over from the Big Bang, a certain pattern in the temperature variations across the night sky. And if we could find those temperature variations, that might give us strong evidence that there was such a collision, that there are other universes out there. So far, we don't have this evidence, but at least shows us that a wild, strange idea, such as other universes, might actually, in principle, be testable. So if these ideas are correct, here's what the universe would look like. You pull out from Earth. You pull out past the other planets in the solar system. You pull out of the Milky Way galaxy. You keep on going. You pull out of the universe, and we'd be one of a grand collection floating in this multiverse. So how do you think about this? Well, let me just give one final remark to place this in context. As I said at the outset, none of my three stories, not the multiple Big Bangs from this theory of cosmology, not the many different shapes for the extra dimensions that comes out of string theory, not even this observation of the accelerated expansion, none of this proves that other universes are out there. It just gives us strong motivation for taking the idea very seriously. And moreover, the idea fits perfectly into a historical pattern that we have seen play out across 5 centuries, right? 500 years ago, the perspective was that the Earth is the center of the universe. Turned out not to be true. We recognized that the planets are all in orbit around the sun. So naturally we thought, okay, the sun is the center of the universe. But then we have another cosmic demotion when we recognize that the sun is one of hundreds of billions of stars in the galaxy. But clearly, the galaxy must be the center of it all, the center of the universe. But then we realize that our galaxy is one of hundreds of billions of galaxies in the observable universe. Perhaps this pattern will continue, leading us to the idea that our universe is not the center either. It's just one of many other universes floating in a much larger cosmic reality. That, to me, is a stunningly exciting idea. And if we're lucky, maybe we'll have some evidence for it in our lifetimes. Thank you very much.